we are going to discuss this 2004 structured essay equation, which is given from magnetic field, right? Which is given from moving coil galvanometer, right? A straight wire carrying a current capital I, it is not L, it is I, is placed in a uniform magnetic field of flux density capital B. A straight wire carrying a current of capital I placed in a uniform magnetic field of flux density capital B, as shown in figure 1. The angle between the directions of the magnetic field and the current is theta. The angle between the direction of the magnetic field and the current is theta. Write down an expression for the magnitude of the magnetic force F acting on a length simple L of the wire in terms of L simple L, capital B and theta. Right, let me show you the figure. This is the figure 1. They ask us to find or write down an expression for the force acting on simple L length of the current carrying conductor. This is the vertical one, is wire is the conductor. It carries a current of capital I. The angle between the wire and the magnetic field is theta, and current flows through the wire. They ask us to find the force acting on simple L length of a wire. What is the equation here? Lamai, F equals the force acting on a current carrying conductor. Somebody give me the equation. So here we should consider the perpendicular component of the magnetic field, right? So perpendicular component is B sine theta. So it should be B sine theta times current is I, length is simple L. That's what they have given, right? So what's it here? We should consider the perpendicular component of the magnetic field. B sine theta is the perpendicular one. You see, you can divide the magnetic field along two perpendicular directions. The component towards the angle cos B cos theta, component away from the angle sine. Right. So we should divide the given field into two perpendicular directions. The field component away from the angle is sine theta. Sine theta. And sine theta is the component which is perpendicular. Cos theta is acting along the line, acting along the wire. Can you identify? So always you should use the perpendicular component of the field to the wire, right? I would like if you write the answer as well as if you draw the figure. If you draw this figure, it will be easy for you to understand the answer, right? Write the answer and draw the figure and mark the two magnetic fields like this. Start. Who wants more time to draw the figure? May I go to next question, Lamai? Please raise your hand up if you want any more time to draw the figure. Right, I'll go to next question, dear. Okay, Lamai. If you want any more time, please take a screenshot. Next question. Simple A, Roman number 1 is BIL cos theta. So BIL sin theta. Roman number 2. Write down the rule that gives the direction of the magnetic force. In the case when theta equals 90 degree. If theta equals 90 degree, there is a rule. We can use that rule to find the magnetic field force. What is the name of the rule, dear, that we use to find the direction of a magnetic field force? Kamai, what is the name of the rule? Okay, one by all the students, say the name of the rule one by one. So it is Fleming's left-hand rule here, right? Write down the rule that gives the direction of the magnetic field force. Roman number 2, that is Fleming's left-hand rule, right? If you say a left-hand rule, it's not enough. And the other thing, write down the rule. So write down the rule means you have to write the rule in words. That's the case. Got it? If you write only the name of the rule, they will not give you full marks. So you have to write the answer like this. Simple A, Roman number 2. Simple A, Roman number 2. Should write the answer in words. Fleming's left-hand rule. Under that, you should write what the rule tells us, right? When the thumb, first finger, second finger of a left hand are kept perpendicular to each other. Are kept perpendicular to each other. Then thumb shows the Lamai. Then thumb shows the, at least a single student. Thumb shows the direction of the force. Thumb shows the direction of the force. First finger. First finger shows the direction of the field. And second finger shows the direction of the current. So this is the rule. Check. Fleming's left-hand rule. When the thumb, first finger, second finger of a left hand are kept perpendicular to each other, then the thumb shows the direction. Then thumb shows the direction of the force. comma, first finger shows the direction of the field, and the second finger shows the direction of the current, FBI. Write the answer for simple A, Roman number 2. Right? Right. Okay, let's go to next question. I think time is enough for you to write. Let's go to next question. Simple B question. Now the above wire is bent to form a rectangular coil PQRS. There was a wire. That wire is bent to make a rectangular coil. Of capital N number of turns, of length simple A, breadth simple B. This coil is placed in a uniform magnetic field of flux density capital B, as shown in figure 2. I'll show you the figure 2. The angle between the plane of the coil and the direction B is simple A. The angle between the plane of the coil and the direction of capital B is A. It is not simple A. Please correct it on your tute. It is alpha. Angle is alpha, not simple A. Eh? A current capital I pass through the coil. Roman number 1. Write down expression for the magnetic force acting on PS and QR of the coil. Write down expressions for the magnetic force acting on the arms PS and QR of the coil at the instant shown in figure 2, and hence derive an expression for the magnitude of the couple acting on the coil in terms of NIB alpha. It's not simple A, alpha, and the area capital A of the coil. Area capital A of the coil. Right? Magnitude of, which means we should find the forces and we should find the couple acting on the coil. So this is what we have done in our theory note. This is what we did in the theory note. Right? So all the things that we have written in the theory note, they ask as a question. Right? Let me show you figure 2. This is figure 2. Right. I would like if you draw this figure 2 because then it is easy for us to answer the question. And we should mark the magnetic field, direction of the magnetic field. You see here, if you consider, it's better to draw the figure. In the exam, no need to draw the figure because figure is already given. Right. So direction of B can be divided in two perpendicular components. The component acting into this direction, cos. Component acting into this direction is sine. Right. So which component is acting perpendicularly? If you consider QR side, perpendicular component is this. Even for P, that is the perpendicular component. So it's very important to mark the divide the direction of the field like this. Right. Even here you can derive it like this. You see, perpendicular component and the parallel component. Okay, dear. Draw this figure and mark these directions. They are essential. The component which is perpendicular to the sides and the components which is parallel to the sides like this of B. Start. I have resolved the magnetic field along two perpendicular directions. Then it is clear that cos alpha component perpendicular to the QR side and cos alpha component perpendicular to PS side. So that is B cos alpha. Cos alpha is the perpendicular component. Here also same. B cos alpha. Draw the figure, Lamai. In the exam, no need to draw the figure, but it will be very much helpful. Even in the exam, you mark these B cos alpha components. B sin alpha parallel to the QR and PQ sides. I'm not going to write them. Okay, I'll mark them also. Right, this is B sin alpha. Here, this is B sin alpha. Sin alpha parallel to the sides, cos alpha perpendicular to the sides. what are the data that they have given here? They have given length, the length and width they have given. Length of the conductor is given as simple A. Am I right here, Lamai? Length is given as simple A meter. Width is given as simple B meter. Please mark them. If you mark these things, it will be very easy for you to understand. So what is the force acting on PS and QR sides? That's what they have asked, right? The forces acting on PS and QR sides. Let's write them. Force acting on PS side. Force on PS side. Because there are many coils. Normal equation is force BIL, but there will be n number of turns. It means n number of wires are there along PS. So force acting on one conductor BIL, force acting on n number of conductor BIL into n. But the perpendicular component is not B. The perpendicular component on QR and PS is B cos alpha. So it should be B cos alpha is the perpendicular component. Right? So your answer should be like this: B cos alpha into I into L. But again, we have a problem. What is it here? If we leave the answer like that, again, we have a problem. What is it? Because length is not simple L. That's the point. Length is not simple L. Right? The normal equation I have written it. What is it? Perpendicular component of the magnetic field to the PQ side. To the PQ side is B cos alpha. I have written B cos alpha ILN. Button length is simple A. So we have write one more step. We have write one more step. What's it? B cos alpha into I into let me mark into I into L. L is simple A into number of turns capital A. So this is the correct answer. Check there, Lamai. So this is the force acting on PS side. Similarly, what is the force acting on PQ side here? We can write it again in the same method. Force on QR side, sorry, Q force acting on QR side, same method, equals BIL is the force acting on one wire. There are capital N number of wires because it says N number of turns. It is said that there are N number of turns in the wire. So BIL into N. The perpendicular component is B cos alpha. Perpendicular component of the magnetic field B cos alpha into capital I into length is simple A, number of turns capital N, like that. This is the method that you have used, right? Check whether you have written both answers. So it means it's very much clear that force acting on each side, PS side and QR side, same force, same. The same force is acting on both sides. Complete there. Please complete your answers. Okay, Lamai. The final thing is the couple. There are two parallel forces acting on the coil, right? The perpendicular distance between the two forces, simple B. So what is the couple acting on the coil? That's what they have asked. The next thing is the couple acting on the coil. What's the definition of a couple here? The torque due to a couple. Lamai? You don't remember mechanics, right? What is the definition? Couple equals a force. A force into perpendicular distance. Perpendicular distance between the forces. One force multiplied by perpendicular distance between the forces. You don't remember. But no need to write this equation here. No need to write the equation in words, right? Perpendicular distance between the forces, right? So a force is B cos alpha, B cos alpha into I into simple A into simple N. Perpendicular distance. The perpendicular distance between the forces is simple B. Simple B. So finally we will get this equals, I'll take the answer to this side. And I manage yes. Finally, we know that simple A into simple B is the cross-section area, right? So finally, I can write the equation in this format. B into I into, I'll write A and B together. A into B written together. A into B into L is BIL into N, capital A, and cos alpha. Cos alpha. Then we will get cross-section area. Length into width is cross-section area. So finally, we will obtain the answer as BI cross-section area into N into cos alpha. Check whether you can understand this, Lamai. Is this clear for all? Right. I think time is enough for you to write. Who wants more time to write the things? Please raise your hand up in the Zoom chat. If anybody wants any more time to write this, please raise your hand up in the Zoom chat. Right. If you want, you may take a screenshot. I'm going to go to the next question. I'll erase. So we have answered simple B, Roman number 1. We have answered simple B, Roman number 1. We have obtained the couple. Roman number 2. The couple due to the magnetic forces on the arms PQ and RS is 0. Explain the reason. Because if you consider PQ means upper bar, right? If you consider the coil like this, if you consider this coil, this rectangular coil, right? If you consider this rectangular coil, this is PQ. This is P. And this is Q. PQ side. And this is R. And S. So if you consider PQ and RS sides, it is very much clear. You can apply Fleming's left-hand rule to the coil. Then you can find that FBI, so force is acting upward. And force acting on SR acting downward. These two forces equal, but the problem is they are acting on the same straight line into the opposite directions. So therefore, these two forces cancelled out. What's the problem there? The forces acting on PQ and RA sides are equal in the direction, are equal in the magnitude, opposite in the direction. As they are acting on the same straight line, the resultant force is zero. Therefore, no torque is formed by the two forces acting on, no couple or no torque formed on the forces acting on PQ and RS. Let me read the question again. Simple B, Roman number 2. The couple due to the magnetic forces on the arms PQ and RS is zero. Explain the reason. Couple mean torque. Torque due to two parallel forces. Right? Please write the reason. The forces acting on PQ and RS sides, the forces acting on PQ and RS sides are equal in magnitude and the opposite in the directions. The forces acting on PQ and RS sides are equal in magnitude and opposite in the directions. And opposite in the directions. And opposite in the directions. Full stop. Equal in the magnitude and opposite in the directions. Full stop. As they are acting along the same straight line, comma, the couple here becomes zero. As they are acting along the same straight line, comma, the couple becomes zero. The couple becomes zero, even the resultant force zero. The couple becomes zero. Now draw this figure saying a knot. Draw this figure saying a knot. This figure will help you to understand the answer further. Can somebody unmute the mic and read the answer for Roman number 2? Somebody please read the answer for Roman number 2.
The forces acting on PQ and RS sides are equal in magnitude and opposite in the directions. As they are acting along the same straight line, the couple here becomes zero.
Thank you, dear. Thank you very much. Draw the figure. So I think time is enough to draw this figure, right? I'm going to go to next question. If you want any more time to draw the figure, please take a screenshot. Right, I'm going to move to the next part of the question. Eileen, it's okay. Simple C question. The figure 3 shows a schematic diagram of a moving coil galvanometer in which the magnetic field is not shown. So we have to go to next page. Ne? Figure 3 shows a schematic diagram of a moving coil galvanometer. Let's go to the next page. They have not shown us the figure. Ne? They have not shown us the figure, but let's read it. Let's read the questions. After we read the question, I'll show you the diagram. First, let's read the questions. This is the schematic diagram of this moving coil galvanometer, right? See, there's a hairspring, spiral hairspring. There's a pointer. There's a scale. This is the coil. To provide the current to a coil, you must use a separate arrangement, right? So you cannot send the current like this. You should use half slip rings. Those things are not drawn. So this is the diagram. What's the missing point of this diagram, dear? Can somebody tell me the things which are very important but not shown in the diagram? Lamai? Magnetic field is not shown, right? Magnetic field is not shown, right? So let's go to the questions. How is the dependence of couple mentioned in simple B Roman number 1 above in this instrument? So it means there's a small mistake in the question, I think. Let me check. How is the dependence of the couple on alpha, not simple A, alpha? How does the dependence of the couple on alpha? Avoided in this instrument. Avoided in this instrument. That word is missing. Here there should be a word avoided in this instrument. Avoided this instrument. How do we avoid the dependence of alpha of the top there? By using a coil is kept in a radial magnetic field. So please write the answer for this. Simple C Roman number 1. By keeping the coil. By keeping the coil in a radial magnetic field. We have explained this very well in the theory class. By keeping the coil in a radial magnetic field. By using a radial, it's not right. By using a radial magnetic right now, okay. By keeping the coil in a radial magnetic field. By keeping the coil in a radial magnetic field, then what will happen? So So the direction of the magnetic fields, not so then the direction, of the magnetic field, then the direction of the magnetic field is acting in the plane, of the coil, for any position, of the coil. This is the complete answer. Then clear. Then cos alpha equals 1. Cos alpha 1 now. Once you multiply all the things by 1, it's not changed. So the cos alpha is 1. So this is the complete answer for Roman number 1. Okay, Lamai? What is the answer for Roman number 1? By keeping the coil in a radial magnetic field, then the direction of the magnetic field is acting in the plane of the coil. Acting along the plane of the coil. Acting along the, oh no, it's okay. Plane of the coil for any position of the coil. Then the cos alpha becomes 1. Because alpha is 0 there. Roman number 2. The galvanometer coil has capital N number of turns and area capital A. The flux density of the field is B. And the spiral has a torsion constant C. When the current capital I, it is not capital L, when the current capital I is flowing through the galvanometer, the deflection of the pointer is theta. They have missed a question. Write down the expression relating I and theta. That's not right. There are many mistakes. Write down the expression relating I and theta. That's the correct question. So forgive me, dear. Write down the expression relating I and theta. So what is the expression which shows the relationship between I and theta, dear? For Roman number 2, right? The coil comes to rest for a certain condition. There are two forces acting on the coil. One force is given by the current in the coil. The other torque is given by the spring. So coil comes to rest, right? Torque given by current. Torque given, right, along the same line. The torque given by the current. When the torque given by the current becomes equal to the torque given by the spring, becomes equal to the torque given by spring, given by the hairspring, then the coil comes to rest. The torque given by the current, we found it as BIL, BIAN. Now cos alpha not there because alpha is always 0 due to the radial magnetic field, BIAN, equals torque given by the spring constant into rotated angle. Here rotated angle is given as theta. BIAN into C theta. So now I can subject capital I. Sorry. I can subject capital I like this. capital I equals, the constant C is there. BAN come to this side. Constant C is there. BAN comes to this side as a division BAN. So it is BAN, and angle theta will be there separately into theta. So this is the expression here, right? Yeah, I have not written theta as theta. Okay, I'll write theta as theta. You see, now it is theta, right? Now it's not 0, it's theta. You see the beauty? Okay, complete. This is the answer for Z Roman number 2. Lamai, what about audio and video, dear? Clear or not clear? Is audio clear, Lamai?
Yes, sir.
What about video, dear? Clear or manageable? Please tell me, dear.
Clear.
If audio is lagging, please tell me. Is audio lagging or clear?
So audio is clear. Video is also clear. Sometimes it's blurry, but it's okay, manageable.
If video is not clear, it's okay. You can adjust it. But if audio is lagging, you must tell me, because I am explaining the things here. So audio is more important. So if audio starts to lag, please send a message to the Zoom chat. Okay, Lamai? You can't learn with the lagging audio. If audio starts to lag, please quickly send a message to the Zoom chat. Okay. Right. Roman number 3. This galvanometer has a full scale deflection of 5 milliampere. Full scale deflection means the maximum current that can be measured by this instrument is 5 milliampere. That's the meaning. How would you connect an external resistor to convert this instrument into an ammeter having full scale deflection of 5 ampere? Wow. First of all, you check whether you have completed this answer, because I want to erase and I need some more space. I'll erase all these things. If you want any more time to write the things, please take a screenshot. I need more space. Right. Look at board here. This galvanometer has a full scale deflection of 5 milliampere. So maximum current that can be measured by this gadget is 5 milliampere. So even we draw, if you want, we can draw an ammeter like this. Galvanometer can be indicated like this. A circle to say the galvanometer, we write capital G inside it. So this is the circuit symbol of a galvanometer. Right. Then we can connect. For example, let's say we directly give this current 5 ampere to this galvanometer. Then what will happen? We give the entire 5 ampere current to the galvanometer directly. Then what will happen? Can you guess? We send this current directly to the galvanometer, 5 ampere. 5 ampere mean how many milliamperes there? Lamai? Five ampere means how many milliamperes? Ah, yes, you know it, right? Good. Now, what do? We give the entire current directly to the galvanometer. 5 ampere means 5,000 milliampere. Then what will happen? Namai? The maximum current that can be sent through the galvanometer is 5 milliampere. We want to measure 5 ampere. So we directly give the 5 ampere to the galvanometer. Then what will happen? Galvanometer it burns. If you send, you can send only 5 milliampere current, but you send 5,000 milliampere current directly to the galvanometer, so it is burnt. It gives you a smoke. So after the experiment, you don't have a galvanometer, you have some ashes and smoke. To avoid this, we connect another resistor like this. We connect a resistor like this. See? We connect a resistor like this. Then what will happen? We select this resistor. Don't draw it, because exam it does not ask you to draw the figure. Right. We connect a capital R resistor like this. Then the galvanometer takes 5 milliampere. Galvanometer takes 5 milliampere. And the remaining current will flow through this resistor. What is the current flows through this external resistor here? 5,000 minus 5. It means 4,995 milliampere current flow through this external resistor. Now it will not be burnt. Can you understand it? So this is the method that we use to protect the galvanometer from higher currents and measure the 5 ampere. Got it? Lamai? I wish to give you a separate note for this even in the theory class. Please remind me to give you a separate note for this. So what is the answer? How do we connect this resistor here? We have connected this resistor parallel to the galvanometer. So what is the answer for the question here? How would you connect an external resistor to convert this instrument to an ammeter having full scale deflection 5 ampere? So we write an external resistor. An external resistor is connected parallel to the galvanometer. This is the answer. An external resistor is connected parallel to the galvanometer. Write your answer. Roman number 5. If the resistance of the galvanometer coil is 20 ohm. Galvanometer means we know the internal structure of a galvanometer. So internally current flows through a galvanometer. Even the circuit symbol is like this. This current flows through a coil. Resistance of that coil is given as 20 ohm. So I can mark internal resistance mean the resistance of the coil, that is 20 ohm, right? 20 ohm, right? Calculate the value of the resistor needed in Roman number 3. Calculate the value of the resistor needed in Roman number 3. Now you have to draw this figure. You should draw the figure for the Roman number 4, not Roman number 3. Just write Roman number 4 and draw this figure. Start. Okay. Draw this figure for Roman number 4. Let me mark the currents as let me mark this current as I1, I1 is 5 milliampere, and let me mark this current as I2, that is 4995 milliampere, and this is I. Keep it like this. I'll divide it to 6, right? Good. Okay. Now you should draw this figure. We need this figure to solve this problem. The current I1 is 5 milliampere. Current I2 4995 milliampere. We should mark two special points saying point X and point Y. We need the 2 points. Draw it. Draw the figure and mark the points X and Y. This is X. This is Y. right? So I hope that you have drawn the figure. The point here is, if you consider point x and y, you can find the potential difference between x and y by considering the upper path. You can go from x to y along the upper path through the galvanometer. If so, potential difference between x and y is the current I1 into resistor simple R. Similarly, you can directly go from x to y along the external resistor capital R. If you go from x to y along the external resistor capital R, then the potential difference between x and y is the current I2 into capital R. Can you understand here? So therefore, potential difference between x and y can be found in two different ways. You can travel from x to y along simple R, or you can travel from x to y along capital R. By applying Ohm's law, V equals IR, the potential difference between x and y, I1 into R, I2 into capital R. But we know that the other thing that we know that this current I1 and I2, the current I1 and I2 should be equal to 5000 milliampere, because 5000 milliampere reaches to x, divided in two sections as I1 and I2. Current coming to the node equals the currents leaving the node. Therefore, 5000 should be equal I1 plus I2. That is Kirchhoff's first law. So whatever the method you use, the potential difference between x and y should be the same. Therefore, I1 into simple R must be equal to I2 into capital R. Right? Whatever the equation you use, you must obtain the same answer for the potential difference between x and y. So I1, we don't know. We don't know what the I1 is. No, we know I1. Yeah, so sorry. I1 is, we know 5 milliampere. We know simple R. Make it 20. I1 5 milliampere, simple R 20. Then I2, it is also known. I2 is 4995 milliampere. I did not convert milliampere into ampere. Why? Because this milli to this milli cancelled out. No need to convert. No need to do any conversion. Right? So then I can take 5400, this 4995 to this side, and this 5 and 20 will be there. So I can subject capital R like this. 5 into 20 units cancelled out, divided by 4995 equals capital R. Now you see, we can divide this 5 and 4995. Right? They can be cancelled out. Then you will get an answer for capital R equals 20 will be there. 49 divide 4 can't divide by 5. 49 divided by 5 is 9. 5 times 9, 45, 4 remaining. Again with this 9, it will be 49. 49 divided by 5 is 9, 45. Again 4 remaining, 4 and 5, 45. 45 divided by 5 is 9. So it means the capital R is 20 divided by 999. So what is this dear? This is approximately 999 is approximately 1000. So 20 divided by 1000 means this 0 and this 0 cancelled out. 20 divided by 2 divided by 100 means 0.00, no, only one 0, 0.2 unit is O. So this round of case is okay even in the exam. Even in the exam, this is okay. So this is the external resistor that you want to connect. Please complete the answer for Roman number 4, dear. Lamai, complete it. Final question. Propose a method to modify this instrument internally, to measure the current in microampere range. So microampere range means sensitivity should be increased. To measure the currents in the microampere range, sensitivity should be increased. Right? To measure the current, in the microampere range, to measure the current in the microampere range, the sensitivity should be increased. Correct? To increase the sensitivity, what should we do here? What are the methods that can be used to increase the sensitivity, Lamai? We should a strong permanent magnet. Strong permanent magnet should be used, or a very thin hairspring. Is used. These are the best two methods to increase the sensitivity. What are the methods to increase? Did I erase that one? Oh, no, I have not erased. I was afraid whether I have erased it. To measure the currents in the microampere range, the sensitivity should be increased. To increase the sensitivity, there are two methods. What are two methods there? A strong permanent magnet is used to increase the magnetic flux density. A strong permanent magnet. They ask internally, how do you modify? So if you say only magnetic flux density is increased, that's not an answer. You should give the method. A strong permanent magnet is used. If you want, you can modify it. Is used to provide larger magnetic flux density. But if you say only providing a higher magnetic flux density, it is an incomplete answer. Right? Okay, dear. So like that, you should give a perfect answer. You should give the methods. Right? A very thin hairspring is used for what? To reduce the value of torsion constant. I think it's given in the torsion constant of the spring. Torsion constant of the spring. Normally we use K, but here they have used, I think, C. So this is a perfect answer. Your answer should be perfect here. Right? So they ask, how do we modify the instrument internally? Right? How do we modify the instrument internally to measure the currents in the microampere range? To measure the currents in the microampere range, sensitivity should be increased. To increase the sensitivity, we have the two best methods. There are some other methods, but these are the two best methods. We should increase the magnetic flux density by using a strong permanent magnet. We should reduce the torsion constant of the spring by using a very thin hairspring. Okay, dear? That's it. So we have completely answered 2004 magnetic field structure essay question, which is given from Galvanometer. Okay, I'm happy.